So last time we finished up rotational motion, centripetal force, and centrifugal force. Now we're going to move into a few more ideas that we can relate back to linear motion, but instead of just things moving in straight lines, we're going to keep going with the idea of rotation. So you'll recall that the simplified statement of Newton's first law is essentially an object at rest tends to stay at rest, while an object in motion tends to stay in motion. There is a rotational equivalent. So an object rotating about an axis tends to remain rotating about the axis unless interfered with by some external influence. So rotating things will continue to rotate. The property of an object to resist changes in a rotational state is called rotational inertia, also called the moment of inertia. So this is the more of the like physics and engineering STEM definition. So I'll probably wind up using them both interchangeably. But the long story made short is essentially bodies that are rotating tend to remain rotating. Non-rotating bodies tend to remain non-rotating. Just like an object in motion stays in motion, although we know if we slide a hockey puck even across ice, it's eventually going to slow down because of friction. Same thing here. Something starts rotating, friction over time is going to slow it down. But if we can remove friction, it'll rotate forever. Just like linear motion, rotational inertia depends on mass. So remember, that's the measurement of laziness of an object. Laziness. More mass means it's harder to get moving or harder to stop. Less mass means it's easier to move or easier to stop. There's an extra thing here that we need to consider. So rotational inertia depends on the distribution of the mass about the axis of rotation. Okay. The greater the distance between an object's mass concentration and the axis, the greater the rotational inertia. So you can see these first two images here. The rotation is happening this way. Okay, which means our axis of rotation is in this person's fist, and they're trying to do this with these dumbbells. So notice that the mass is close to the axis of rotation here in this first example. But then in the second example, they're much further away. That's why it becomes difficult to rotate. So if you want something easy to rotate, you want to get your masses as close to the axis of rotation as possible. Otherwise, you're going to have a bad time. The greater the rotational inertia of an object, the greater the difficulty in changing its rotational state. You actually see this if you will, before Barnum and Bailey stopped doing their thing, back when it was not politically incorrect to go to circuses, you could see tightrope walkers hold these huge poles that were 20, 30 feet long. They're massive. And while they were walking across the tightrope, they would keep these in their hands and they'd keep them level. So the whole idea is that if you use this very long pole, you could actually use it for balance, because your axis of rotation is sort of around this point, right? Your axis of rotation, it sort of makes a circle around the tightrope itself. And if you hold this very long pole, you've got these two long lengths of mass on each side. So the whole idea is you can use it to steady yourself, because if you start rotating it, it's going to fight you. It's got a lot of inertia because it's so long and so massive. So the whole point is the shorter these large sticks are as you're walking across the tightrope, the harder it is to actually keep your balance. And that's just due to how hard it is to rotate those long ones. The rotation or the rotational inertia of any object actually depends on the axis that it rotates about. So if rotational inertia, if more rotational inertia means something is harder to rotate, let's think about these three examples with these pencils. So this way, you'll notice this is just a rotation around essentially the pencil lead, and I can do that with my iPad. See, look, this is the easy one, right? I can do this so fast. This is the axis of rotation going through the pen. That's easy. Okay, well, let's look at B. This one's a little bit harder. I can't do a full circle, but I can wiggle it, right? That's going to give me a partial rotation. So it turns out this is a little bit harder than this, right? So I can do this all I want to. That's easy. This is a little harder because I have more mass and more length. So I have more mass away from my axis of rotation. Now, if I move to option C here, and I essentially try to rotate it this way, I can do it this way. Rotating it this way, this is actually really hard. I suggest you all try it with your own pens and pencils. But this, you can feel a big difference because here's my axis of rotation. Now I have all this mass with all this distance away from my axis of rotation. And this is actually, it's hard to move if you just want to use your fingers. You can actually see the same idea if you play baseball. So a long baseball bat held near its narrow end, where you would hold a baseball bat, actually has more rotational inertia than a short bat. Okay, so if you want to be a heavy hitter, you want to get as much mass away from you as you can. That means the bat is going to be really hard to swing, but it's going to make you a heavy hitter because there's so much mass, so much inertia there. Um, Once you get a long bat swinging, it has a greater tendency to keep swinging, but it is harder to bring that up to speed. A short bat is easier to swing. So if you look and see where the axis of rotation is here on both bats, if you start back here and maximize the length of your bat, look at what the speed is. You get like a max speed here on the tip of 90. This is your tangential velocity. So you can see your tangential velocity depends on R. We'll even change this. Depends on R. Essentially, as you increase your radius from your axis of rotation, you increase your speed, right? Because you start 10 miles per hour down near your hand and you get up to 90 miles per hour at the end. So this is spinning it on the very end. But if you just leave a little dangly bit back here, you'll notice you get a velocity in the opposite direction. But look at what happens. You get an even faster tangential velocity. That's because you shorten the bat, so there's less mass way out there. You can get it up to speed faster. So that's why you're going to get 100 miles per hour instead of just 90. If you're interested, I think there's some exercise science majors in this class. So I do have a sports article here. It's the physics of choking up, and essentially just the old phrase choke up on the bat. There's a whole article here about the physics behind when to do that and why to do that. If you're interested, you can check it out. So keeping along with this idea of rotational inertia and what's easy to roll or swing and what's hard, it's precisely because of rotational inertia that a solid cylinder starting from rest will roll down an incline faster than a hoop. And you can see that here. So this has a bigger velocity than the hoop. Both rotate about a central axis, and the shape that has the most of its mass far from its axis is the hoop. So we have a central axis here. Both of these have a central axis. Now, if you think about it, they both have some sort of mass. Well, the hoop's mass, it's all pushed away. And if you remember, did we talk about this? Where is it? We haven't used an equation yet, but we have all this mass far away. So all M1 is far away from center. Okay, all the mass is far away. That's going to make it hard to rotate. But here, all of mass 2 is just, it's sort of, it's not all pushed out. Some of it's really close. So the mass here is going to be easy to rotate, right? Only the mass on the outside is hard. So this is hard to rotate, easy to rotate. All this is hard. No matter what you do, it's all on the outside. So we'll say that all of M2 is distributed. Distributed, there we go. So for its weight, a hoop has a greater rotational inertia, and it's harder to start rolling and harder to stop rolling. So this is wild. This is wild. So any solid cylinder will outroll any hoop on the same incline. Turns out it doesn't matter if the masses are the same or not. Isn't that wild? Two completely different masses. So like these masses up here, you could have a very heavy solid cylinder, a very light hoop, or vice versa. It doesn't matter what the masses are. They're the solid one is going to outroll the hoop every time. I think that's really weird because you would think that the mass has some sort of input. And now I'm going to really confuse you because here is how we actually calculate how much inertia something has. So you can see different shaped objects have different moments of inertia. You can think of just different amounts of inertia. So we did talk about a hoop rolling around a horizontal axis, right? So in the previous example, that would just be the inertia, I is mr squared. And then we were comparing that to essentially a solid disk or a solid cylinder, and that's 1/2 mr squared. So you see that the hoop has more inertia, right? The hoop is mr squared, but the disk from the previous slide is actually 1/2 of that. So the disk has less inertia. Now, here's the thing that bugs me. You see M in here. See, both of these have an M. But when these two things race, it doesn't matter if the masses are the same or not. So there's an M in the equation. But at the end of the day, when you roll these down the hill, the M doesn't matter. The question is why? So I'm going to do some math that might be a little hard to follow. You don't have to know this for the problem sets or labs, but I do want to explain what happens. So if you think about anything rolling down a hill or an incline, it's going to have some initial gravitational potential energy, right? GPE. Then it's going to roll down the hill. So this GPE gets turned into something else. What does it get turned into? Okay, well, it gets turned into kinetic energy coming down. But we're not just sliding down anymore. We're actually moving down. It has a motion, a linear motion, and it's also rotating. So we also have rotational energy. Now, the idea here is that we can take our MGH that we talked about in the last module, our gravitational potential energy. We know some of that's going to go into kinetic energy, 1/2 mv squared. And then you don't have to remember this. I'm just going to give it to you. Our rotational energy is 1/2 I omega squared. Now, remember, if you look at these, all of these moments of inertia, they all have an mr squared in them, but even though they all have m r squared in them, they just have a different number out front, right? So for whatever thing we're talking about, I'm just going to say a mr squared. And then if we're talking about a hoop or a sphere or a disk, we can just replace this a with whatever coefficient is out front. So the whole idea here is mgh, gravitational potential energy, is split between our kinetic energy plus 1/2, here comes my substitution, our moment of inertia, omega squared. Now, here's the freaky thing. Every term in here has an m, so the mass cancels. And it turns out your whole energy equation, gh equals 1/2 v squared plus 1/2, well, 1/2 a r squared omega squared. No mass is in there. So it turns out when you think about the energy of these things, the mass actually does cancel out and it doesn't matter. So that's why when you're racing these things, you can have two objects, two different masses, and still you can go by these distributions for inertia, right? The hoop will always come in last. The disc or the solid cylinder will always beat the hoop, no matter if they weigh the same or not. It's weird. Let's move on to this example. All right, so if we balance a hammer upright on the tip of your finger, the head is likely heavier than the handle. Sure, okay. It is easier to balance with the end of the handle on your fingertip with the head on top. Okay, is it easier to balance with the head on your fingertip with the head or with the head on top or the other way around? So essentially, which one of these is going to be easier to balance? Well, it would make sense to stand the hammer with the handle on your fingertip, right? So handle on the fingertip, and the head away and at the top, like this. It will have a greater rotational inertia. So you've got more mass up here at the top, and you've got more mass far away from this point of rotation. And that's going to make it harder to actually tip over. So this is the way you'd want to do it. All right, moving on to torque. So we talked about how hard it is to get something to move in a circle. Let's talk about the thing that actually causes the movement itself. So torque is actually the counterpart of force. Remember, force pushes something, causes an acceleration, causes a change in motion. Well, torque essentially causes things to rotate. Okay? So it's just like a force, but we're going to go around instead of front and back. So if you want to make a stationary object move or a moving object change its velocity, you would apply a force. So let's look at this. A stationary object move, a moving object change its velocity, that has to do with force. If we want to make a stationary object rotate or change its rotational velocity, we apply a torque. So both rotational inertia and torque involve distance from the axis of rotation. Okay, so again, we're going to have this R in here. In the case of torque, this distance, which provides leverage, is called the lever. Okay, so obviously with this seesaw, these kids are applying torque to the seesaw. We have to think about where this lever arm is on the seesaw and how we measure it. So the lever arm is the shortest distance between the applied force and the rotational axis. Okay, and for that reason, we can define torque as the product of the lever arm and the force. Okay, so that means we need to figure out how to define a lever arm and exactly what force is causing the torque. And then just to cover everything, notice that the units are the lever arm, or the length of a lever arm, which is going to be a distance, so meters, times a force, which we know is in newtons. So our units of a torque are Newton meters. Okay, so let's look up here at this first example. It looks like here's our axis of rotation because it's just a seesaw, teeter totter, whatever you like to call it. So there's our axis of rotation, and we have one lever arm here, right? So this is one lever arm of 3 meters. We also have another lever arm over here because it just has to go to the force. So this is our second lever arm of 1.5 meters. So there's our R's, our lever arms. Okay, now we just need to mark the force that's actually causing these torques. So here we have a weight of 250 newtons. So this will be mass 1. And over here we have a second mass, S2, with a weight of 500 newtons. So there's our forces that's causing the torque. Okay, we'll do the calculations later. We just need to identify the things. Something to note, this guy, well, let me do black. Here we go. This guy wants, his torque is pushing this way. You could call this positive direction. The girl's torque is pushing this way, right? So it's clockwise versus counterclockwise. One wants to go this way, the other wants to go the opposite direction. So the whole idea is we need to come up with a positive direction, negative direction. These two are canceling each other out. So there's no movement. They're canceling each other out. So we know that the torques are equal and opposite. Something to point out here. In this next situation, everything's pretty much the same, except we've moved the seesaw up on a cliff. And just because this girl is now 5 meters away from this axis of rotation, that does not mean that the lever arm is 5 meters now. That's not the lever. You always have to look at where the force is applied. So the lever arm is still 3 meters. It hasn't changed. So be aware, make sure you don't accidentally come up with the wrong radius when you're doing these problems. So the lever arm about any axis of rotation is the perpendicular distance from the axis to the line along which the force acts. Okay, so let's look at this first picture. So notice this hand is at an angle, and that actually causes the force vector to be at an angle. So it turns out this is not the lever arm, because it's always at a right angle and it's always got to intersect the line of force. Okay, so here is our right angle intersecting the line of force. So it turns out our lever arm is actually short. Okay, so we lose a bit in our torque. Right, so our torque is the lever arm times the force. Well, here our lever arm is short, right? That's not helpful. Now, if we move our wrist and actually make a 90-degree angle, we actually get more torque this way because our lever arm becomes longer. If we put a pipe over our branch, we get even more torque because we extend our lever arm. So we go from a baby R lever arm to a slightly bigger lever arm to a really big lever arm, right? So we keep increasing in our torque equation. We keep increasing the R. We get more torque out of it. So let's look at this example. So if a pipe effectively extends a wrench, just like we saw here, if a pipe effectively extends a wrench handle to 3 times its length, so R becomes 3R, by how much will the torque increase for the same applied force? So our F in our equation, F stays the same. This becomes 3R. So what's that going to do to our torque? Well, luckily, these are some simple calculations. So 3 times more leverage. So if we multiply one side by 3, it's an equation, we have to multiply the other side by 3. So 3 times more leverage produces 3 times more torque. Now we've got the net torque on a body or on a system. This must also be 0 for mechanical equilibrium to be achieved. And essentially, this just means you add up all the torques and it has to equal 0. And by the way, this is a tau, is a Greek letter. And that's what we use for torque. So add up all the torques and it equals 0, no rotation occurs. So let's go back to this boy and girl in mechanical equilibrium. Let's show that they are actually in mechanical equilibrium. So the girl, we know that she's going to be rotating in the negative direction. The dude here is going to be rotating in the positive direction. So we'll go ahead and throw in a negative sign for the girl. So we know we have some radius and we have the force. The force is her weight. So we have the radius or the lever arm length is 3 meters. Her weight is 250 newtons, and that's going to equal negative 750 newton meters. So in this direction, we have negative 750 newton meters. Now the boy, same thing. His lever arm shorter, 1.5 meters, and he also weighs more. He weighs 500 newton. So his rotation this way, his torque is 750 newton meters, but it's positive. So if we add the girl's negative 750 to the boy's positive 750, we get to show that this is in fact in equilibrium. We can also talk about center of mass. So for any given body, the center of mass is essentially the average position of all the mass that makes up the object. So we can take, when we're talking about spinning something, right, it's going to want to spin around its center of mass. And if we were to take this object and just smash it down into just a tiny point, that's what the center of mass would be. So we got 2 options over here. We have a cone, we have this triangle, and essentially here is the center of mass for both of these objects. That's the dead center of both of these. And you can calculate, these are pretty easy because they're standard shapes, but if you get a weird shape and you need to calculate the center of mass, you pretty much have to resort to calculus and some crazy calculations. But just know that for simple objects, you can approximate them or take something complex and pretend it's a simple object, and you can get some easy calculations for center of mass. So a symmetrical object such as a ball, it's going to have its center of mass and its geometric center. That makes sense. The ball is perfectly round. Its center of mass would be right dead center. Smash it all down at once. You just got a smaller ball, essentially. But an irregularly shaped object, such as a baseball bat, may have more mass toward one end or the other. Center of gravity is also sometimes used to talk about center of mass. So center of gravity and center of mass, they can be different, but for everyday objects on the Earth's surface, they're pretty much the same thing. So you could, as long as you're on Earth and it's an everyday object, you could actually talk about center of gravity and center of mass being the same thing. So note that the center of mass of this sliding wrench down here is indicated by the white dot. And I'm going to try, see if I can show that. So here's the center of mass all the way across. You'll notice that it actually follows a very straight line while the whole rest of the wrench is actually rotating. So the center of mass is actually the natural axis of rotation for this object. If you throw a wrench, it's going to naturally spin around its center of mass, right? So the center of mass is going to be a dead straight line, but everything, the whole rest of the object is going to rotate around. Since there's no external force acting on this wrench, The center of mass moves in equal distances in the time intervals. So you'll notice when I mark these, they're pretty much evenly spaced. So you can tell that this is a constant velocity. So we actually have two different types of motion here. We have this straight line motion, so the center of mass is moving linearly. And then we also, on top of the center of mass linear motion, we have this rotation. So obviously we've caused some sort of torque here, and then the torque is causing the rotation around the center of mass. It's just the natural way that, or the natural point that something's going to rotate about. So if the wrench were instead tossed in the air, no matter how it rotates, its center of mass will follow a smooth parabolic arc while the body is rotating. And this is true for any object. You can see that here in these two pictures. You can't see it because it's a nice, perfectly spherical ball, but the center of mass is here with the orange dots, and the ball is likely rotating, and it's rotating about its center of mass. It's more obvious with the bat over here. So if this guy throws his bat, you can see the center of mass pointed out by these orange dots, but while the center of mass follows this nice, pretty arc, this bat is also, the body itself is rotating while the center of mass follows a much simpler path. This sort of begs the question, can an object have more than one center of mass? And the answer is no. If it's a rigid body and it's not some crazy weird thing, it's essentially going to have just one center of mass that you can calculate. The center of mass for any uniform object, like this meter stick, is essentially the balanced point where you can support the entire weight of the object with just this one point. Okay, and it's a balanced rotation. If you think about how gravity is acting on this ruler, you've got all these force vectors. All of this is weight, mass pulling down. If you can get all the mass over here to equal all the mass on the other side, what you'll see is all of the mass and the weight added up on the right-hand side, trying to rotate it in the positive direction, is going to have an equal and opposite counterpart trying to rotate it in the negative direction. So it turns out, once you get to this balanced point, the center of mass, all these little tiny torques from all the individual pieces of the ruler, when you add it up to get the weight, you're actually going to cancel each other out. So the net torque is zero. The center of mass of gravity of any freely suspended object actually is just directly beneath the suspension point if you take any object and hang it up. This is weird. This is like a double word. So just the center of mass, that'll be much better to understand. So the center of mass of any freely suspended object lies directly beneath the suspension point when the object is hanging. So here you can see we're hanging the US up on this point, and we're using this vertical piece of string. Let me use a different color. We're using this vertical piece of string to essentially trace out these paths. If you do this for essentially 2 points, so to determine where the center of mass is for a weird object like this, you just draw a vertical line, just like I did here in orange, and then you essentially just move over to a new point or a new suspension point and draw another line. You can see this has already happened. So someone has hung this little decal up, drew a vertical line, then hung it up here, drew another vertical line, and the idea is wherever these vertical lines intersect, that's going to be your center of mass. Do keep in mind, if you think about this boomerang, the center of mass doesn't have to be inside the object. You can totally have a center of mass outside the object. That's actually why the boomerang looks weird when someone throws it. It's because its point of rotation isn't actually on the object itself. just to think about the whole center of mass thing a little bit more in stability, if we have whatever object and you draw a straight line down from its center of mass, if the straight line you draw falls within the base of the object, then the object is not going to tip over. It's in stable equilibrium. It will balance. So you can see here, even though the leaning tower of Pisa is leaning, if you determine its center of mass and draw your arrow down, it falls within the base, so it's stable. If you try to do yoga and you touch your toes, you've got your center of mass here, it falls within your base. So this lady is good to go. She's not going to fall over. But if she backs up against the wall, and I encourage y'all to try this, if she gets her heels and legs up against the wall and tries to touch her toes, she can't move her center of mass over enough. So now she's unstable. Her center of mass is no longer over her base. And you can see here in this picture, here's this guy's base. It's a very small base, so this takes some practice. But if this is his base, that means his center of mass needs to be right over the top of his hands, which are acting as a base. If you can do that, you can hold yourself up like this indefinitely, as long as you don't, as long as your arms don't give out. You can do it till you get tired. But it takes a lot of work to make sure you keep your center of mass right over this really small base you give yourself, because your base is only as big as your hands. But if you can do it, you can essentially balance. You'll have two torques acting in opposite directions, but they'll be equal and they'll cancel each other out. All right, let's see. Yes, so I'm going to stop here. We'll save angular momentum for the last little bit. This last one should be a short lecture, and it'll be the cool thing that I was talked about it last time that got me interested in physics.